reference that it's looking at. That is the most common, the easiest way to traverse a linked list. And so I use it for the size and the print list, but you can use it for anything. In fact, you're probably going to use that for your homework assignments. All right, we all pretty good with this? We don't have a lot of time, but let's go ahead and do the removeAt. I'm going to go a little bit quicker with this one because of time constraints. But I think now that we've seen this one, the removal is very similar, but obviously it's different because we're removing. So in this situation, by the way, this is an important thing to know. When our insertAt method terminates, its stack frame goes away. And that means that our temp and our, what did I call it here, our new node, those references were in the stack frame. And so they actually go away, leaving the list all alone. Okay, it's just sort of a fun fact. All right, now for the removeAt, we have almost the same procedure. It's just that the end result is different. So in this situation, we have the same pair of initial problems. If they want to remove at a negative position, we cannot do that. If they want to remove at position 0, fine. We just call removeAt. We can always do that, assuming that it's there. We still do have to check to see if it's null. So the removeAt, we can simply call and have that be our answer. We still need to move to position -1. That has not changed, because if we want to remove this node, we have to get to this node and point around it. All right, so we still have to get to the position ahead of the one we are dealing with. But then at the end, we don't create a new node and insert it. All right, oh, and by the way, if we hit null, we can't remove because we ran out of items. But instead, once we get to the element that's ahead of it, we just set that element's next to point around it. All right, and that's kind of funny. I'll show you how that actually works. All right, and that is to point past it. That did not fit on the screen. There we go. All right, so that's what we want to do. Let's get to the code, and it's going to be very similar, so it should not be too tricky for us to write. We've got a few things, and look at all that code. I mean, the insertAt with comments, it's a pretty hefty chunk of code just to do this. And in this situation, we don't need a value. We only need the position, right? So we're just removing at this position, whatever. And so let's get through our fundamental stuff. If position is less than 0, return false. If position is equal to 0, this one is a little bit different because we're not going to removeAt and return true, because it's possible that the removeAt 0 will fail. So I'm going to return what I get from removeAt. All right, pretty tricky, huh? If that fails, we'll return the failure. If it works, we'll return true, that it succeeded. And so now we need to move into our position again, just like we did before. So we'll set up int I equals 0 and node temp equals head, right? We're just setting up our traversal while loop, and with the same set of parameters, while temp is not equal to null, right? We're fine as far as that goes. Yes, it should be removeAt and not removeAt0. That was a typo. Thank you for chatting that to me. Nice catch, Ashwan. I appreciate you saving me the trouble of finding that the hard way. Good man. All right. And then so long as I is less than position -1, because the moment it becomes position -1, we want to stop. And again, we have I++, and we have temp equals temp dot next, doing our classic traversal. And then again, if temp is equal to null, it gave us a bad value for the position, it's too big. In this situation, we have one other possible failure point that I forgot to mention. If we are at the end of the list and they wanted to remove this position, we can't. And so I need to do one other small check, and it just dawned on me that I didn't have this in the code that I gave you, so I'll fix that. If temp is equal to null, or temp dot next is equal to null. If temp next is equal to null, then there is nothing to remove. And I'm just looking at the code that I gave you, and I forgot to put that one little bit in. So I'll fix that. And so now in this situation, we are ready to remove from wherever we are, and we do that simply by doing this, temp dot next, right? That's holding the node we want to remove. We set it equal to temp dot next dot next. Okay, and then we return true. So let's talk about this temp next equals temp dot next and why I can pull that off. All right. So as we move through our list, we're going to cause our temp to be pointing at items. Let's pretend, just for argument's sake, that we wanted to remove this one. And so temp is looking here, right? If that's the case, we want to set this pointer to look at this one. This reference is called temp next, and temp next is looking at this node. This node's next is at dot next, so we say temp dot next, and that's that one. So when we set temp next equal to temp next dot next, we're actually setting it equal to that, and it will go around it. And this node is now no longer in the list, and so it's removed. Now, if we happen to be removing the last node, so this node's gone, garbage collected because we're in Java. If we were removing the next node, this temp next would be equal to temp next dot next, which would be null, which is perfect because the end of the list is supposed to be null. So this would become null, and I can draw a null without almost falling out of my chair. And when we set that equal to null, quite possibly the ugliest null I've ever drawn, then this one is not referenced, and this one is the end of the list. So we're finished. And so that is how the removeAt works. And I apologize for making the typo in the stuff I gave you. I'll send a corrected version out with an announcement. Any last questions? Because this is all I had planned on covering for today. Please type in chat. Give me a thumbs up if everything is cool. All right, I will stop recording.